Okay, perfect. Thank you. Hi, everybody. I'd like to first thank the organizers for letting me give this talk, and second, thank you all for being here to listen to me. So I will be presenting some of my research that I've done at Carleton College about facilitating the visual comparison of clonal trees under a variety of different distance measures. Now, a lot of this context that I will be providing next, you will have seen already if you attended the keynote just a couple hours before, but you just have a head start then, so bear with me. Okay, so first, just thinking about cancer as an evolutionary process, we begin with normal healthy cells. Then some cell will acquire a mutation and begin to replicate. I'm representing a mutation here as that orange square, and that could be, for instance, a point mutation like this C2A, or it could be some other kind of mutation. Now, as that cell continues to replicate, more mutations will be acquired and will provide further selective advantages for these cancerous cells. Here, these cells are, all of those different shapes are mutations, and different lineages are beginning to emerge. Finally, this leads to the uncontrolled growth of these cells, which leads to the formation of a tumor. Now, we call all of the groups of cells that have the same sets of mutations within them clones, which I've illustrated with these blobs here. And basically, those would be relevant of how we're thinking about the way that these lineages within the tumor have evolved. Now to think about basically how can we put the data in a way or put this evolutionary trajectory in a way that we can both compare and analyze, because we'd want to be able to compare how different tumors have developed in order to better understand the ways in which cancer can progress. So this brings me to the way that we commonly represent it, which is through clonal trees. So basically what these show is how the different lineages of clones have evolved over time. So here each node is a clone, and you can see that that is the same evolutionary history represented. However, you will note that since that orange square mutation was kind of the initial mutation to occur, it is then inherited by all of the ancestor or all of the descendant nodes. So there's some redundancy then encoded. So we typically then instead represent just with each label is just the new mutation that has been acquired. You'll also notice down in that bottom right with that green diamond and purple pentagon, you'll see that two mutations can be kind of shown to have been acquired at the same time, which could biologically happen, but more often is kind of the result of having to infer the evolutionary history from data taken from a single point in time. So when inference methods are ambivalent about the order of which those mutations came in, then they will cluster them like this. This underlines kind of the importance of being able to compare these clonal trees, because then if you want to be able to evaluate whether your inferred tree method is accurate and effective, then you would want to be able to look at simulated data that has a ground truth and be able to compare whether your inferred trees are sufficiently representing it. So that's clonal evolution, and now that brings me to thinking about distance measures, like how can we actually compare these trees? So to walk you through a bit on this, I'll be working with these two very small example trees. Now the mutations are labeled with letters on the nodes rather than shapes, but it's the same idea. And you'll notice that both of these trees have the same set of mutations, but their topologies are different. So one simple distance measure is parent-child distance, which I'll walk you through. And basically, you take the set of parent-child pairs on both trees, and then you find the symmetric difference, which is basically all of those relationships that occur in one tree but not the other for both of those trees. And then the total size of that resulting set is the distance. So this is distance 4 between tree 1 and tree 2. Distances are outputted distances that are closer to 0 or are more similar. Larger numbers are more different. However, this kind of distance measure, given that it outputs just a single distance, is limited in some ways in being able to kind of discern the ways in which these trees are different from each other. For instance, if we introduce this third tree, tree 3, we see now that all 3 of these trees are equidistant from each other. However, tree 1 and tree 3 have identical topologies, but just their root and their leaf node mutations are flipped, whereas tree 2 has a very different topology. This, however, this distance measure is now imparting that all 3 of these trees are different from each other at the same distance, even though the more nuanced ways that we can see when we're looking at the topologies are different. So there are other distance measures you could use that emphasize different pieces when they're calculating their distance. For instance, here's ancestor-descendant, which is similar concept to parent-child, except instead of calculating the symmetric difference between parent-child relationships, it's between ancestral relationships. So it's a more global measurement. And here it finds that those 2 trees with the same topology are much more different. However, overall, no distance measure that outputs a single number as a distance is free from this sort of limitation of just the single value. So overall, there's a lot of distance measures that have been recently developed, and they emphasize different features, which then they can be used better in different situations depending on the context. And they are very globally useful for determining similarity and difference. However, they do all output a single value, which makes it challenging to identify the nuanced structural differences between the trees. And that's the gap that we are seeking to address with the development of our tool. So now that brings me to actually introducing our tool, which is entitled VECTr, and I'll be looking at 2 trees on breast cancer data. So here's our tool. There's kind of 3 main visualization components. First, we have our node link diagram. Then we have our heat map and our tripartite graph. To just speak a little bit more in depth about our node link diagram, we have several encodings here, but the edge encodings stand out most prominently, with the darker edges being more contribution and the lighter edges being less. And this visualization is very helpful because it's a familiar way of representing trees, and you're able to kind of more globally see where are the areas of similarity and difference. So then moving on to our heat map, this encodes basically the space of all of the possible mutation-mutation relationships, and it shows a summary of every change that has taken place between the 2 trees. So if we were thinking about looking at how has F4, the relationships that it has, changed between the 2 trees, we could look basically in its row and column to see. And orange squares represent that the relationship is present in tree 1, while purple is present in tree 2. And finally, thinking about our tripartite graph, we can see that here this is more zoomed in on capturing just the changing relationships around each individual mutation. So the way that you read this is down that central column, and any mutation to the left of the column is basically parental to that central column, and then those mutations on the right are its children. So if we think about zooming in on one single mutation, we can then see the shape of all of those mutations to the right, which are parental to F4, and then its 2 children over there on the right in the 2 different trees. Okay, so that brings me then to, that was an introduction to the pieces of our tool, and now I'll kind of introduce sort of a type of use case and some of the features you could see it. And now I'll be looking at trees from colorectal cancer. So here is those 2 trees pulled up, and immediately you'll see that there are basically 2 2 main areas of difference on those 2 node link diagrams. And that is then mirrored over here in our other 2 visualizations. So then you might kind of, if we were wanting to focus more on what's going on down towards the leaves, we could kind of hover over one of those mutations and see how basically all of those visualizations respond to that. So we could look through a couple of them, and then once we identify a mutation that we might want to better understand the biological significance of, we've linked to the gene cards so you could have ease of access to that. So Another way to more explicitly spell out how the tripartite graph might be used, if we're thinking about kind of this more localized area of higher difference up by the root, we could think about APC1, which is kind of in the central there in tree 1. And we can see that over here on the tripartite graph, that CDK4 is an orange edge that is parental in tree 1, whereas it is a child of APC1 in tree 2. So this indicates that there's some sort of basically lineage rearrangement of those nodes, which is likely causing that main contribution in that area of the node link. And it's much easier to parse out why that mutation is causing a higher contribution when you can look at the tripartite graph rather than just trying to compare between the two trees in our node link diagram. And then APC1 also, we rank how much each mutation contributes, and it's the top contributor in this case. Now, there are a couple other pieces. We could look at these trees under a variety of different distance measures, like here it is on ancestor descendant. And we also, linking back to what I was talking about at the beginning, can use basically set one of those two trees that we've inputted as a ground truth. So this would be coming back to thinking about being able to evaluate how inference methods are working. And basically, if we set one to be correct, then on the other one, we can see all the ways in which that other inferred tree has errors. So that kind of wraps up the bulk of my talk. Some of the future directions we're thinking about would be implementing other distance measures or thinking about more rigorously enhancing the ways in which our tool could help aid evaluation of inference methods. And now I'd like to thank my advisors, Layla and Eric, as well as Kwok, who worked on this project a lot with me, as well as Mohammed El-Kabir, who is at University of Illinois, who gave us invaluable feedback early on in the project. And that's my email, and we have all of our code up on this GitHub link. Thank you.